Hi everybody, welcome back. This is the first of 5 of these quick overviews on the light board of all the classes that you've taken, SC0x to SC4x. So let's start, and I want to focus and just give a high-level view of what you learned in SC0x. SC0x is kind of like the toolbox. It's all the methods and techniques you need for the rest of the courses as well as the rest of your career. It's meant to be very quantitative. We do it up front because you use these techniques throughout the 5 courses, as you certainly saw. The biggest thing that I think you take away, though, and the biggest thing we focused on, was the mathematical dexterity. Some of you who've taken this course had been out of college for a while, you hadn't really done stuff, and so we had to reintroduce you to functions, because everything we do deals with mathematical functions. We talked about approximations and different ways to come up with different answers. And we had exact methods and approximate methods. We talked about all those things. So the real Trojan horse, the thing we're trying to make sure you were able to get throughout SC0x is this first one. Are you able to handle mathematical equations? Can you do the analysis? Can you do the modeling? Then we introduced 3 sets of tools, really. The first one is optimization. And so we started with unconstrained optimization, where you're looking for an extreme solution of one of these functions, right? If I have a function like this, I want to find a minimum, or I might have a function that looks like this, and I want to find a maximum, whether I'm maximizing profit, minimizing cost, and you have something that y is a function of x. And for unconstrained optimization, we showed you about first order conditions, where if I take the derivative of that and set it equal to 0, then I'm solving for that x, that variable that gives me the optimal, the extreme solution. And we used this in SC0x, actually, when we developed the economic order quantity, or EOQ. It's just a first order condition of an unconstrained optimization that lets me determine the optimal quantity to order to minimize cost. So we started with unconstrained, and then we moved quickly into constrained optimization, and we spent a lot of time later in SC2x using these tools. And so this is where you have some objective function, z equals, f sub x, some function, and it's always subject to a series of constraints. And so some kind of constraints, and where a and b are constants, and your x is greater than equal to 0. So you have an objective function here, you have a series of constraints, and again, what we're doing here, I have these constraints, and I have this objective function I'm trying to find, say, the maximum point, and the big takeaway we learned is that it happens at the extreme points in a convex space. So what do you need to take away from this? Well, you should be able to recognize how to do unconstrained optimization. It's just taking a first order condition and setting it to 0, and you should be comfortable using linear programming to do this and recognize the constraints, the strengths, and the weaknesses of using this technique. Because again, you use these throughout the other courses. Then we moved in and we changed things, because this is all deterministic. There is no variability, and we allowed stochasticity or randomness to enter. And so we focused in initially on probability, getting you to understand what does it mean to have a probability of something. And then we dove right into distributions. And so the big granddaddies that we focused on were the normal distribution. And we used this a lot later on in SC1x when we looked at inventory, and this is where you have some mean and some standard deviation. We also focused in on one of my favorite distributions, the triangle distribution, where you have a minimum, a maximum, and a mode. And so this is a triangle distribution. And then we also spent time using the Poisson, and this is a discrete distribution, which means it only takes integer values, 0 or greater. And it's a function of lambda, which is the mean and the variance of the distribution. So we use Poisson a lot when we dealt with small distributions, like very slow-moving parts. We used normal distribution for almost every situation in inventory. It's an easy, well-established distribution. And triangle distribution is really good when you're not symmetric, when you have a long tail. I use it a lot for transit times when I'm trying to model how long does it take for a piece to get across the ocean, because physics stops you on the left side but you can have really long delays. So you don't have a symmetric distribution. That's one of the problems with a normal. You're symmetric, you're bell-shaped. Anyway, so we talked about distributions. We talked about how to take empirical data, how to fit the distribution, and we also tied into some inference testing. And we mainly focused on hypothesis testing. We did some sampling. We talked about how to set up correlations, but we used this really to test hypotheses. Did this new software improve sales? Did the sales get increase more when I ran this marketing campaign? So it lets you do hypothesis testing, and you get to prove or show whether you had an effect or not. The last thing we did was focus in on regression and simulation. These are two tools that kind of tie together. Regression is all about taking empirical data, the observations, and trying to fit some kind of relationship to it. And we focused mainly on ordinary least squares, where you're trying to fit a line where this y is a function of x, where this is y, this is x, and it's going to be equal to some constant plus some slope beta 1 times x. And the idea is I'm going to use my real data to estimate these beta terms. And so we use this a lot in practice because you're trying to have real data and you're trying to understand, well, what's the relationship? How do I fit this into my other systems? We use this for forecasting. We use this for collecting data to feed into models. We use this a lot to capture, say, rates of transportation to see what affects the transportation. Regression is probably one of the most widely used techniques in our thesis projects just to make sense of real data to be able to use it into one of these models. And then we finished up with simulation. And simulation, we did a discrete event simulation. We did Monte Carlo, a bunch of techniques. To be honest, we're not going to be able to test the actual running of simulation models on the CFX. They're too large, too complicated. They don't fit within the framework of the CFX because it's a very limited, tight time. But you need to understand the pros, the cons, and some of the details in the concepts. So this is what you learned in SC0x. Again, it's a toolbox, a set of tools that you can use going forward in all the 5 courses as well as the rest of your career. So good luck studying.